I think my volume is already loud. I don't know why. So related to in-person lectures, and then setting the changes. It's not easy. So I cannot find volume controller here. Okay. So I will use this mic. Okay. So now we can have in-person lectures also. So because midterm exam period passed. So and then you can see. So I can see some students' face in this classroom. So it's good. Then I believe some students already know. So I posted the midterm exam scores on the Blackboard. So you can check the Blackboard skill. You can check the midterm scores in the Blackboard. Also, if you want to check your exam, like exam paper, then you can visit TA's office. Okay? And then please note that we will not return your exam paper. Okay, so in the previous class, we learned how to design control unit in the pipeline architecture. So the first we start from the how to design pipeline stages. So we learned that we can split each stage of a pipeline architecture with pipeline registers. Okay. So the pipeline registers are just D flip-flops. So which means that some signals are sampled by clock signals. So like this. So this is the D flip-flop. Also, like the single cycle processor, the pipeline processor also requires control unit. And then you can generate control signals from instructions. Okay? So control unit is here because we can decode instructions in the ID stage. That is the instruction decoding stage. The instruction signal is here, and then this signal. So this instruction is given to control unit, and then control signals can be generated. And then these control signals are the same to the control signals of a single cycle processor. Okay, and then so these control signals need to be delivered to the data path elements. Each data path element has a control port, and then control signals need to be delivered to the control port of a data path element. So, but in the pipeline architecture, we already know that some data path elements located in different pipeline stages. So, for example, ALU is in the EX stage, and then also ALU received control signals. So, which means that control signals are generated in the ID stage, but because the ALU is in the EX stage, the control signals for this ALU is required, and the instruction is in the EX stage also. So which means that the control signals also have the same kind of this instruction. So which means that if control signals are required in the EX stage, which means that the control signals also need to go through the pipeline register. Okay, this is very, very important in the pipelining design. So we need with the timing of the data, which means instruction, and then also we with the timing of the control signals in the pipeline architecture. Also, it covers the early part of the data forwarding. So which means that, so this is the pipeline architecture. So which means we need to detect data dependencies between instructions. Why? So we need to build the data forwarding unit and hazard detection unit. So we already learned that in the pipeline architecture, those clock cycles can be wasted because of data hazard. And then we already know that the data hazards are caused by data dependencies between instructions, like A equal 1 and B equal A plus C. So which means that the value of A should be delivered to the next instruction or next statement. So we can avoid wasted clock cycles with data forwarding first. So if the former instruction is arithmetic instructions, then the result of this arithmetic instruction can be forwarded to the next instruction. Okay. Also, if the former instruction is lower, then which means that the data is read from data memory. So in the memory stage. So in this case, if the very next instruction requires the result from load instruction, then we cannot forward this data to the EX stage because the data is read from the memory, and then this data is stabilized after this memory stage, like here. So in this case, we cannot make use of data forwarding path in the pipeline architecture, which means that the next instruction should be stored in the pipeline processor, and then one clock cycle is wasted. So we need to control data forwarding and hazard detection, which means that we also need to control pipeline stalls if the load use hazard is detected. Okay, so we require these two control units, like data forwarding unit and hazard detection unit. Okay, so I have already explained about the data forwarding and how the data forwarding can be performed in the pipeline architecture here. So people explain about the conditions of data forwarding. So let's see how to implement data forwarding path. Okay. So, okay, let's start here. So in the previous class, I already explained that. So the result is generated by formal arithmetic or logical instructions. So in this example, the solve instruction generates the result, and then the following instructions receive result from solve instruction. Okay, so in this case, so if you see the following instructions, so we can know that following instructions require operands. So actually, these instructions AND or some AND. Also, these instructions need to read data from register file. But we already know that actually these instructions use ALU, so which means that if the required data is ready before these operands are processed by ALU, and it's okay. Which means that the required data can be forwarded to the input of ALU. Okay, so if we see the ALU structure, actually in the single cycle processor, so I believe you already will remember some connections between register file and ALU. So this is the register file, and then so this is the ALU. So the output port of register is connected to the input port of ALU. Also, another output port of the register file is connected to the ALU. But we already know that the second input port of the ALU also received the immediate value. So there is a MUX, it's a multiplexer. Then we need to select the output of this multiplexer between the output of register file and immediate value. So which means that we need to generate the control signal, the selection signal for this MUX. So this is the how register file and ALU are connected to each other. Okay, but in the pipeline architecture, in order to implement data forwarding path, so we learned that the output of the formal instruction should be delivered to the input of ALU. So which means ALU can receive its input from register file, is a normal case. Also the folded result. Okay, so there can be two different cases, that's actually three. So one input can be from register file, and then another input can be folded from formal instructions, like the result of formal instructions. So there can be multiple inputs, and then we need to select from these multiple inputs. So which means that we need multiplexer for this ALU. And then this figure shows how the forwarding path can be implemented in the pipeline architecture. So if you see that this forwarding path, so we can find that, oh, this is the register file output for the RS1, and then this RS1 is connected to this, okay, here. So it's the RS1 out, and then, so we already learned that one of the input of this ALU can be forwarded from output of EX and memory pipeline register. So if you see this register, so you can find that this register received the output of ALU here, and also this register is sampled by clock signal. And then the right edge of the clock is output of ALU is sampled by clock signal, and then it becomes the output of this pipeline register. So this value can be forwarded to the input of ALU. So this is this case. Okay, like so the result of sub instruction is here, and then this data is forwarded to the input of ALU for this end instruction. So this is the forwarding path for this case. Okay, so if you see that this forwarding path, so you can find that this forwarding path is connected to the here. So here, this point. So you can see the connection here. Also, another forwarding path is this one. Okay. So, and the sub instruction is in the write back stage, and the result of ALU is here after this memory and write back pipeline register, and then this value can be also forwarded to the input of ALU for this oral instruction. Okay, so which means that we need to forward the result in write back. So what is the result in write back? So can we or this result or this result or this result. As you can see, the output of this multiplexer is forwarded to the input of ALU. So as you can see, this forwarding path is connected to the another input of multiplexer. So it is because the output of data memory and also the output of ALU are selected by this multiplexer. So which means that the output of this multiplexer is the result in write backstage. So there can be two results. So one of the result is the result from ALU. So another result is the result from data memory. So and then we need to select the write back result from the data memory output and the ALU output. So which means that this is the final result of the write back stage. So this result is forwarded to the input of the multiplexer. So just focus on this multiplexer. So this multiplexer has three inputs. So one of the inputs comes from the register file. This is the normal case. And then for the forwarding case, so there are two forwarding paths. So one forwarding path is from the result in the write back stages. So that means that actually this is the output of memory and write back pipeline registers. But we can say that this is the result in write back stage. So this is the result in write back stage. Also, another forwarding path is that this is the result in memory stage. So this is just the output of the execution and memory pipeline register. Okay. So here is the more also. So this result can be forwarded to the another input of ALU, right? So which means that so this another input here. So this B is A. So input B over ALU also received one input from the output from the register file here, and then it's the result of the write back, and then this is the result from memory staging. Okay, so we need, which means that we need two data forwarding multiplexers because ALU receives two operands, two inputs. Okay, so here and here. Oh, but you can find that. So actually, in the single-cycle processor, there is another input here. So this input receives the immediate data, also the output from the register. So what this multiplexer is hidden in this figure, but actually also in the pipeline, the architecture of the pipeline, the processor, we require this multiplexer. Okay, and then this multiplexer is actually located here. So one of the input comes from the output of this multiplexer, and then another is the immediate data. Okay, but this multiplexer is hidden in this figure because this figure just explains how to implement forwarding path. Okay. So if you see this forwarding path, so we build, so in this figure we build forwarding path. And then as you can see, this is the multiplexer, and the multiplexer requires selection signals. Which means that we need to generate the selection signals here. So it's forward A and forward B. So which means that we need to generate these control signals using another control unit, and that this control unit is called forwarding here. Then, how can we generate these selection signals? So we can generate the selection signals by conditions. So which means that if this folding path is required, we can activate this path. Or if this folding path is required, we can activate this folding path by detecting folding conditions. Okay. So we need to generate the fold A and fold B control signals, and then these signals are generated by folding. Okay. And how can we generate these folding control signals? Okay. Then, in order to generate the control signals, then we need to detect the folding conditions. And then, the folding, so we can detect these folding conditions easily. Okay, how? When the data folding is required, if the next instruction, the following instruction requires the result of a former instruction, then we need to fold the result of the former instruction, which means that what is the result of the former instruction? This is the RD of former instruction. So this is the result of a former instruction. And then if the RD of a former instruction is same to the RS, the source register of following instruction, then we need to forward this RD to the RS1 or RS2 of following instructions. Okay? Then so we can figure out the conditions of this folding path. Okay? So like this. So in the here. So in the pipeline architecture, the ID is forwarded to the EX stage and memory stage and write back stage. So this is because ID is required for write back operation, right? So we already learned that this ID is delivered to the EX stage, memory stage, and write back stage. Okay, then so we can check the ID here. Then we can check the RS of the following instruction. But when? Which RS? So the first we need to check that when the data forwarding is required. So what does it mean? So we already learned that if a certain control signal is required in a certain stage, which means that if a certain operation is done in a certain stage, then we require the control signal for this stage. So which means that, so like the ALU, so ALU source is also the control signal, but the ALU source is required in EX stage because this signal is required by ALU, which means that the control signals are also delivered to the EX stage. And then folding controls is also the same. And the folding is required. Actually, data folding is required in EX stage. Why? Because the data, as you can see, the folding box is located in the EX stage, so which means that we need to generate the control signals for this folding box in the EX stage, right? So, it is processed in the EX stage, so which means that we need to check the RS1 or RS2 of the following instructions, the next instruction in the EX stage, right? Then, how can you know the RSM RS1 or RS2 in the EX stage. So like this. So this is the RS1, this is the RS2 in the ID stage. So if we propagate the RS1 or RS2 from ID stage to the EX stage, we can get the RS1 or RS2 of EX stage. Okay, so that is the output of ID slash EX dot RS1. So output of the ID EX pipeline register. So we can check the RS1 of the instruction in EX stage. And how about the RD? So RD is the destination register of formal instruction. So which means that the formal instruction can be in the memory stage, like here, which means that when the end instruction receives the data from the sub instruction, then sub instruction is in the memory stage and the end instruction is in the EX stage. So which means that we need to check the RD of memory stage because the formal instruction is in the memory stage. How about the sub and OR? So in this case, OR receives the result of sub instruction in the EX stage, but the sub instruction is in the write back stage. So which means that we need to check the RD in the write back stage and the RS1 or RS2 in the EX stage. Understand? This is very important. So in order to check the data coding conditions, we need to check the ID of the output of ID. So ID of output of EX and memory pipeline register, which means that this is the ID in memory stage. Understand? So this is the output of EX and memory pipeline register. Then we need to check this ID with the RS1. Also, this ID can be checked with the RS2 in the EX stage. Okay? How about another case? This is the ID in write back stage. Also, we need to check the ID in write back stage with the RS1 or RS2 in the EX stage. Okay? We can check the ID and EX stage like this. And so in this case, we need to forward RD to the input of ALU. So which means that the result in the memory is forwarded to the ALU. In this case, it is one case, case number 1. And then for the case number 2, we need to forward the ID of write back to the input of ALU. Understand? So this is the forwarding case, and then it's simple. Okay, but we need to check the corner cases. So what does it mean? So sometimes, so we can get RD from instruction, but for some instruction, so some instruction does not write data to the register file. So like the write instruction, also the store instruction. So these instructions do not write data to the register file, which means that the file instructions cannot use data from these instructions. So how can you know if the instruction write data to the register file or not? We can check the read write signal. Okay? If the read write signal is 1, which means that the corresponding instruction write result to the destination register. If not, the data is not written back to the register file. So which means that even though we also need to check the read write signal. If the red light signal is 1 and if this condition is met, then we can detect the data forwarding conditions. And then another corner case is the destination RD is 0. Like at x0, x1, x2. So in this case, even though the data is written back to the zero register, x0, this is the 0 register, but this result is not updated to the x0. Right. So this is the add instruction, which means that the red light signal of this instruction will be 1 because this is add instruction. But the destination register is x0. So in this case, we cannot, well, we may not. So which means that, so is it okay to forward data to the next instruction like this one? So add x0, x1, x2, and then sub x4, x0, x3. So in this case, we already know that the x0 is not updated by add instruction. Then can we forward the result of this add instruction to the following sub instruction? Is it okay or not? Is it possible or not? So can we forward the result of x1 plus x2 to the sub instruction?
해도 문제는 없는데 굳이 할 필요가 없네.
Really? So it means that it's not harmful if we forward this result to the sub instruction, like here. No, absolutely not. Because in the instructions and architecture manual, the output of x0 is always 0. So which means that even though x1 plus x2 has the non-zero value, so this sub instruction uses the x0 here, so it should be 0. So which means that we must avoid data forwarding in this case. Okay, you understand? 그렇죠. x가 0. 그러니까 데스티네이션이 x가 x0일 때 그때 문제가 되는 거죠. So what does that mean? So if you see this case, so its regularity is 1, and then RD is also RS1 of the EX stage. RD in memory is RS1 of the EX stage. So it means that in which this condition, but we need to avoid data forwarding in this case. We must, okay? If we forward the data to the sub, then it will be very harmful, actually. So which means that we need to check the x0 of RD. And then if the RD is x0, then we avoid the condition. We need to avoid. Okay? So if you see, so this is the forwarding path in the pipeline register. And then you see that. So we can decide the forwarding selection signal like this. Like if the port A is 0, then this is the normal case. So the source is the output of the ID EX pipeline register, which means the output of register file. And then if the port A is 10, then you can see, so it's 0, and this is the EX map. This is the 10, and then this is So this is a 0, 0, 1, 0, and 0, 1. Right? So in this case, if the folding selection signal is 1, 0, then the data is folded from the memory stage. So it's the output of the EX and memory pipeline system. Also, if the folding selection signal is 0, 1, then it's the result of write back is folded to the input of ALU. Then it's sent to the port B. Okay. So we check the folding conditions, like this is the basic condition, so we need to check the regular, also we need to check the X0. But we need to check another corner case, like this case. So if you see that this code example, so we can know that, so actually this is, we can activate the folding from instruction 1, instruction 3. So we can activate the folding from 1 to instruction 1 to instruction 2, so add 1 to add 2. But problem is the add 3. So what's the matter? If we just check the folding conditions like this, and then this, and then this, so then we can find that there can be 2 folding paths. Understand? So which means that if we just check the folding path conditions in this slide page and then this slide page, then we can find that in this case, the data can be folded from the instruction number 1, so as number 1. Also, the data can be folded from 2 to 3. Right. Then, which folding path is the correct path? A and B. You need to select. You need to select from these 2 folding paths. So which one is the correct path?
B.
It's B, because this X1 is the latest result. What do you mean? It's like this: A equal 1, A equal 2, B equal B plus C. So in this case, if we write the code like this, then this A is the 2, right? Because this is the latest value. It's same to this example. So which means that there are 2 possible folding paths here from edge number 1 and from edge number 2. But you know, this X1 is the latest, which means that we need to use the folding path B, not A. So here. So what does that mean? So this, we need to also detect this double folding condition, and then if the double folding condition is detected, then we need to select this folding path, which means that if when we detect the folding path, and then we can find that write back to the EX folding is also possible, and then memory to EX folding is possible. It's okay, and it's okay. So in this case, it's a double folding. So in this case, it's actually double data hazard. So in this case, we need to select this condition, this path. Okay, because this is the latest value, latest output. So this is the revised folding condition considering the double data hazard. So which means that also we need to check this condition, double data hazard condition. Okay? Understand? Okay. So this is the completed boarding path in the pipeline processor. So so boarding unit is here because the boarding is performed in the EX stage. So which means that this boarding unit receives RS1 and RS2 in the EX stage. Also, this RS1 and RS2 of EX stages are compared with the RD in memory stage and write back stage. Also, we need to check the read write signal. Also, we check the ID if XA. So the destination register is 0. So we need to also check the double layer header conditions. Then this boarding unit generates the control signals. It's a MUX selection signal here. So then based on this MUX selection signals, and one of these input is delivered to the input of ALU. So this is the boarding unit in the 5-stage pipeline architecture. Understand? Okay. Okay. Before moving on the next topic, let's take the topics. So currently it's 2:44. So I will give a time until 2:47. Okay. So it's a pub quiz. In this case, so what unites the memory is that instruction memory and data memory are merged into one memory. Okay? Okay, so okay. So next topic is the hazard detection unit. So we learned how to implement the data boarding path in the pipeline architecture, and then also another required control unit is the hazard detection unit. So if the formal instruction is the load instruction, so it means that So we want to avoid this case, but one clock cycle should be wasted because the result of the load instruction is generated in the data memory. So in this case, okay, like this case, the former instruction is the load instruction, and then the destination register is the X2. So you know this X2 is generated after the data memory, like here. But this, so you know, this result is stabilized at the rising edge of the clock. So which means that actually we can use this data in the write back stage. Okay, so which means that when this result is in the write back stage, then this data can be forwarded to the input of ALU, and then before that, we cannot use this data, right? So in this example, the add instruction, this AND instruction requires result from load instruction. So, and then you know this AND instruction requires result in the EX stage, but when the AND this is the normal case. But if the AND instruction is in the EX stage, the load instruction is in the memory stage. So the result is not read from the data memory yet. So which means that at CC5, when the result of load instruction is in the write back stage, and the instruction is in the EX stage, then we can forward this data to the input of ALU, which means that when the AND instruction is in the here, then we need to stop propagation of this AND instruction to the EX stage because the former instruction is in the load instruction, and then AND instruction requires data from load instruction. Okay, so in the load use hazard is detected, then the next instruction, which means that following instruction need to be stored, which means that it's stopped. So stored in the ID stage, because this following instruction requires data in the EX stage, but if this instruction is propagated to the EX stage, but the data is not ready, so which means that this instruction cannot use data. So this instruction needs to be wait in the ID stage. This is called pipeline store. It's called pipeline store. So the meaning of the store is it's a temporary stop. The stop temporarily. Okay? So means that the clock cycles are just wasted, but the instruction stores in the certain pipeline stage. And then what does that mean? So when the end instruction is in the ID stage, then this end instruction should be stored in the ID stage. But this is the pipelining, which means that the following instruction or instruction is in the instruction fetch stage. But because end instruction is stored in the ID stage, this or instruction cannot be propagated to the ID stage also. Right? Because the or instruction is stopped, which means that the following instruction also need to be stopped. This is the pipeline stores. So we need to implement this control in the 5-stage pipeline architecture. So it's the same. So first, we need to define some control path for this load use data header, and then we need to define some detection conditions for this load use data header, then define the control signals. So I already explained that the load use hazard is detected. The instruction, the following instruction need to be stored in the ID stage. So which means that we need to generate the store control signal of the ID stage. Also, it is required in the ID stage because before, actually in the instruction fetch stage, we cannot figure out which instruction is fetched because instruction is not decoded. So, and then also, which means, so we cannot control the pipeline stores in the instruction fetch stage. So let's see the data path, the hazard detection. So as I explained, the instruction is stored in the ID stage. So which means that the control signals are generated in the ID stage. Okay. So which means hazard detection unit. This is also the control unit for hazard control. So this hazard detection unit is also located in the ID stage. Okay. So then how can we control the operation of this pipeline processor? So if the hazard is detected, the instruction in ID is stored. Also, another instruction in instruction fetch is stored. How about the EX stage? So which means that in this example of AND is here, and then OR instruction is here, and AND instruction and OR instruction. So actually, LD is here. So firstly, the load instruction is here, AND instruction is here, and OR instruction is here. And then the load use hazard is detected, and the AND instruction is in the ID stage, and then load instruction is in the EX stage. Okay, then the ID instruction is stored. So after one clock, load instruction is propagated to the memory stage to read data memory. How about the EX stage? It's nothing. So no operation actually. So in the EX stage, this processor does nothing. And then actually this operation is called no operation. So it is frequently called NOP, NOP, so no operation. Sometimes it is called NOP, but we frequently use NOP, no operation. So which means that ORA is stored in the instruction fetch stage and is stored in the ID stage. Then in the EX stage, the processor does nothing, so which means that it's no operation. And then load instruction is in the data in the memory stage. Okay. So and then the next clock, load instruction is in the memory and is in the write back stage. Oops. Then how about this case? So actually we already consumed one clock because of load use hazard, which means that this AND instruction can be propagated to the EX stage. So the pipelines are working. So which means that the NOP is here, It was in the EX stage, and then end is here, and then or is here. So it's possible because when the load instruction is in the write back stage, for this data, the result of a load instruction can be forwarded, right? So in this, we just add the NOP for the EX stage, and then we can, and the instruction can receive data from load instruction. That's how the load with hazard is detected, and then pipeline is stored, and then pipeline is resumed after the pipeline stores. So I will explain that when the end instruction is here, there's a value instruction, and then load instruction is in the EX stage, then we need to check the data hazard in the ID stage. How can we check the data hazard? It's the same. It's very similar to the data forwarding unit. So when the pipeline is stored, first condition is that the formal instruction is load. So which means that it's the instruction in EX stage is load. It's loaded. It's the first condition, and then which means RD of write back, EX stage, because it's a load. EX stage is sent to the RS1 or RS2 of ID stage, because the hazard is detected in the ID stage. And then, this is the load instruction, so we don't need to check the read write. Okay. So we can. So then, how can we check this load instruction? So we can check the memory. Okay. And then also we can check the RD and then RS1. Okay. So this is the hazard condition, the load use hazard condition. So in this case, the pipeline is stored, then the code also bubble. It's the NOP. Okay. Then how can we enable pipeline stores? First, when the pipeline is stored, then we need to first generate the NOP in EX stage, and then we need to store instruction fetch and instruction decoding stages. First, how can we generate NOP? It's a bubble. So NOP means that the processor does nothing. So which means, so and then in the chapter 2, I already explained that when an instruction is executed, then this instruction changes register and memory, right? Then the register is updated by read write signal. Also, memory is updated by mem write signal. Also, we can change the program counter by branch. So we can check the branch instruction. What does that mean? If read write signal is 1, then register is updated. And if the memory write signal is 1, then memory is updated. And if the branch is 1, which means that this code instruction is branch instruction, which means that the result, based on the result of the branch instruction, the program count can be updated. Which means if the control, a certain control signal is 1, then states of this processor are updated. Which means if the all control signals are zeros, then the states of processors are not updated. Then how can you implement NOP? We can implement NOP by forcing zeros to the all control signals. Okay? So it's NOP. So first, control values all zeros. Then how can you force zeros to the EX stage? So the pipeline in the pipeline control unit, the control signals are generated in the ID stage, and then these control signals are propagated to the EX stage by IDEX control, IDEX pipeline registers. And then if we force zeros for these pipeline control signals, then EX becomes the node. So you can force zeros to the this IDEX pipeline registers for control signals. We can generate node. It's okay. How can you store instruction batch and then ID stages? So store means that the instructions stay in a certain stages. So in this case, so in this example, where is the example? So M is in the instruction decode stage, and then OR is in the instruction fetch stage. Then, so actually we give zeros to the EX stage. So here, then how can you store ID stage? So if the OR instruction is in the instruction fetch stage, and then for the normal case, which means that the pipelines are not stored, and then for the normal case, at the 1 clock, this OR instruction needs to be propagated to the ID stage. We need to avoid this case, right? How can you avoid? So we actually the first class of the chapter 4 we learn about the enabled deflector. Do you remember? So it's enabled deflector. So which means that if the enable is 1 at the rising edge of the clock, the output of the deflector clock is updated by input signal. But if the enable signal is 0, the output signal is not updated by input signal. So that is the enabled deflector. So we can use the enabled deflector. So which means that in order to store instruction in the ID stage, we just give the 0 for the enable signal. And then we can use the enabled deflector for the instruction fetch and ID pipeline registers. Okay. So by doing this OR instruction is not propagated, and then the end instruction is maintained in the ID stage. So do you understand it? Do you understand? So we can use the enabled deflector, and then we can give 0 for this enable signal. And how about the instruction fetch stage? So simply for the instruction fetch stage, if we do not update program counter, then instruction is not updated, right? If the program counter has the same value, then the same address is given to the instruction memory, and the instruction memory is generating the same output. Which means that not to store the instruction in the instruction fetch stage, then we can just maintain the program counter value. So that's it. So we can implement the pipeline stores in the ID stage and instruction fetch stage. Okay. Then we can, as you can see, you can find the output of hazard detection unit. So what is the output of hazard detection unit? Sorry. So you can find this pass also, this pass. Okay. So if you see the this pass, actually this is the input instruction fetch ID right. So, but even though this is the right signal, is the same to the enable signal of the deep right. So if the right is 1, then the signal is propagated to the ID stage. Then if the right is 0, the signal is not propagated. So this is the enable signal. And then if the hazard is detected, then this signal becomes the 0. How about the push, right? This is also enable signal for program counter. So program counter is also similar to the deep loop, and if this right signal becomes 0, and program counter is not updated, the old value is maintained, and the old value is just given to the instruction memory, and then this instruction memory is generating the same instruction. That's how the instruction fetch stage is stored. And then, if you see the input of the hazard detection unit here, then you can find that another output. So sorry. So another output of the hazard detection is the false 0 to the EX stage. Here, so you can find that you can find the 0 here, and you can find MOX here. So which means that if this signal is activated, so it's a 1, then all control signals become zeros. Okay? So then we can generate loop in the EX stage. So these are outputs of hazard detection unit. And then in order to detect the hazard, then this hazard detection unit receives RS1 and RS2 here. So it receives mem read in the EX stage and RD in the EX stage. Okay, by checking load instruction and RD and the RS1 and RS2 of ID stage, and we can check hazard. So this is a little bit tricky part in the pipeline resistors. So you know the pipelining is very simple. Because we just split the required stages, and then every instruction is propagated to next stage at the rising edge of the clock, and that's it. And then we using this, then we can improve the performance. Oh, it's easy, but not to implement precise. How can you say the correct pipeline processor? Then we need actually. In order to improve the performance of a pipeline processor, then we need to implement the data forwarding path. The data is dependent. Then, which means that we need to implement the data forwarding unit. Also, for the load user hazard detection case, load user hazard case, then we need to detect the load user hazard, and then which means that we need to also control the pipeline stores in the pipeline architecture. So it is a little bit tricky. So it's the somewhat difficult part of the pipeline pipelining design. Okay. So actually, the basic concept is very simple, but in order to build the correct pipeline processor, they need to consider some complex conditions. Okay, so we already learned that by adjusting the order of the instruction, then we can improve the performance. But if we cannot adjust the order of the instructions, then the hazard is detected, and just one clock is wasted. Okay. So I think I need to stop here because we don't have enough time to discuss the next topic, the control hazard. Okay, so this is the end of the today's class. Any questions? Okay, try to understand how the data coding unit is implemented, and then the hazard detection unit is implemented. Actually, so you will be requested to design a pipeline processor, and then I believe the most difficult part is to build the hazard detection unit and data coding unit. Okay? Try to understand this part. Yes, so thank you for your attention, and then see you in the next class. Thank you, guys.